Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
We're very glad to have Krista Svor here to give a talk on quantum computing. She expects her PhD in computer science from Columbia University in spring 2006. Her research has concentrated on quantum compilers, quantum fault tolerance, and quantum error correction. But her technical interests include the broader fields of data mining, intrusion detection, and classical fault tolerance. So in her research, she has developed the first layered software architecture for quantum computers that maps a high-level program into fault-tolerant machine-level instructions. She has also developed methods to analyze and simulate the reliability of quantum circuits, including error correction circuits. Using a one-class support vector machines to detect anomalies, she has also developed a new host-based intrusion detection system for Windows registry anomaly detection. So, Krista.
Thank you. So, hello. Thank you for the introduction, and thank you for having me here today to speak about my research. Today, I want to try to answer the question, is scalable, reliable quantum computation possible? So I first got into quantum computing several years ago when I was at Princeton, and I was taking a course from Andrew Wiles, and it was a cryptography seminar. And we had been discussing RSA, the RSA cryptosystem, and how it was based on the inability to factor the product of two large primes quickly. And this is why it was secure. And then one day during discussion, someone brought up the fact that there was this algorithm out there that was fairly recent at the time, a few years old, that was developed by Peter Shor, that actually was able to perform factorization in polynomial time. And this astonished everyone in the course. And we all said, oh, we want to learn more. What is quantum computing? What is this device? And why does it have so much power? So I began to look at quantum computing and have focused on quantum computation for my PhD research. So as I said, Shor developed this algorithm to factor the product of two large primes in polynomial time. And this has been the killer application of quantum computers, once we have one, of course. And DARPA developed the quantum factoring challenge for the quantum computing community to look at. And this is to factor a 128-bit number on a quantum computer in 30 seconds or less. So we know that factoring is integral to security. And the question is, how much of a reality is this? Can quantum devices, or when will quantum devices actually be able to perform this task? And today I want to talk about that reality and what we need, what are the steps to actually achieve a scalable quantum device.
Just clarification, RSA primes are like 1,000 bits these days, or?
Yes. Okay. At least.
At least, yeah.
So this is still a third problem.
Yeah, no, but not quantum.
Right, so this is just the DARPA challenge problem. Obviously, we're not using a 128-bit number in RSA. But the idea is just to be able to get a quantum device making the steps towards something that can then, you need thousands more qubits to factor a larger number. So we just want to make the first steps to actually having a device that can do something reasonable beyond factoring 15, which is what we can do now.
In fact, if you could factor 128-bit number, there's absolutely no guarantee that the technology would scale up to 2,000 bits.
Correct, right.
If you couldn't, that's guaranteed you couldn't.
Right. This is a good first step.
Well, if they factored a 4-bit number.
Yes, especially 4-bit number.
Right. Which, no guarantees.
Number is a special form, not a general process.
Right. So as we know, we have a classical algorithm that can perform factorization, but it's an exponential time algorithm. And this is using the number field sieve. So if we want to factor a 512-bit number classically, it's going to take 8,400 MIPS years, about. And then a 1024-bit number is going to take 1.6 billion times longer. So clearly this is not practical. But with a quantum algorithm, using Shor's algorithm, the complexity is now polynomial time. And we can factor a 512-bit number in 3.5 hours, and then a 1024-bit number in about 31 hours. Question?
Here's those numbers.
So this is using a quantum architecture based on an ion trap device, several layers of quantum error correction, and a 1 gigahertz clock rate. Of course, this device does not exist currently, but these are an outlook for what it could potentially do. So we have Shor's algorithm, but we currently don't have a device. So in order to make Shor's algorithm a reality, we need a scalable quantum computing device. We need a design flow that takes this quantum algorithm written in a high-level language and then maps it to a fault-tolerant implementation of the machine instructions to perform on the quantum device. Then, in order to have this design flow, we need languages and compilers and different software tools in order to support this design flow. And then finally, we need fault tolerance and quantum error correction. In order to achieve reliability in our computation. Now, of course, the second and third bullets, these are things we need for classical computing as well. The key is we also need to incorporate fault tolerance and quantum error correction into this design flow. Yes?
Given that, off the top of my head, I can count maybe 3 algorithms that people ever want to implement in one computer. Do you need the languages, the high-level programming language, and the compiler and so on? Why can't you hand machine code in effect these algorithms to your architecture?
Well, you could. I mean, people now are hand machine coding. But the idea is that you want something, you want to be able, maybe with a high-level language, it would give you more insight into how to create more quantum algorithms. And then this process, adding optimization is very key in a quantum computer. We have such limited resources. So if we can automatically optimize a quantum circuit before passing it to the machine, that would be ideal, reducing the number of qubits required or reducing the time required to perform the algorithm. So these things, with an optimization phases, would be helpful.
Yeah, but presumably you wouldn't want completely general purpose optimization to work there. You'd want to hand tool your optimization to
Sure,
apply
for
your
a
problem.
particular device, particular gate set. Yeah, you'd hand tool optimizations for different cost functions, but those could carry over to different devices and different circuits.
Yeah, but in particular for these particular algorithms. In other words, in practice, you want to build this to factory. You don't want to build this to do, accounting, for
Right.
accounting for.
Right, it's going to be a special purpose device, but
So then, all right, go ahead.
all right, so we have Shor's algorithm, and this is Shor's algorithm written in pseudocode. And you see in the black type, these are operations that are performed on a classical device. So we have classical pre and post processing, and then the red instruction order is the operation that is actually performed on the quantum device. So you can see that the essence of Shor's algorithm, or the insight that Shor had, was that he was able to reduce factoring to order finding, and he knew that using a quantum device, which can only perform unitary transforms and measurement, so it has to be completely reversible, using a quantum device, he was able to perform order finding quickly, or in polynomial time. And so with this insight, he was able to then perform factoring. So you can see that this is indicative of the computing environment that we're going to need in quantum computation, and also the programming environment that we require. So we require in quantum computing that we have an environment that can support the interspersing of classical and quantum instructions, as you see here. Now, in order to be able to run Shor's algorithm on a quantum device, we have to be able to now translate this into machine instructions for a particular device or for a technology simulator. So we need a language, we need a high-level language, we need intermediate representations, and we also need compilers in order to accomplish this translation down to the actual physical device. And this is what I'd like to talk about. So what I've done with Al Aho, Andrew Cross, Ike Chuang, and Igor Markov is I've developed a design flow that takes a quantum program written in a high-level language and then translates it down to machine instructions to actually run on a quantum device or technology simulator. Now you can see that this design flow for computer scientists, this looks very standard. It looks like a traditional compiler. So we have a standard front end, which really is similar to the standard front end in a traditional compiler, where we translate into an intermediate representation. But then from this point on, the details of each of these boxes, these phases, are very different than what you find in a classical compiler. So now we have an intermediate representation, which is not like 3-address code anymore. This is now something based on the quantum circuit model, which now abstracts quantum mechanics and linear algebra. We then have the optimization phases, both technology-independent and technology-dependent optimization phases, which again have to work on the abstraction of a quantum circuit. And then we have a physical operations language, which takes into account the details of the actual device you're going to be running your algorithm on, which we then eventually pass to the actual simulator or quantum device. And so the key in computer science is, the goal of computer science is to provide abstractions for more difficult problems. So we take into account, we abstract the quantum algorithm into the high-level language, and then the intermediate representations provide the abstraction of a quantum circuit, and then finally the machine instructions for the quantum device. So already we've taken a problem that was fairly straightforward in the classical setting, and now we have very different details in these different phases of this design flow. So what are the benefits of this type of software architecture? Well, since we have languages and intermediate representations predefined, this means that we can have tool interoperability. It's easy to add and maintain the tools, and we can have wider community participation. So we have defined interfaces where, for example, at MIT, they're working on building a device simulator for the ion trap. They can now work on this independently of, for example, Igor Markov, who works on circuit optimizations at the University of Michigan. So these people can each work on these different tools independently, and then because we have defined intermediate representations and interfaces, we can then put these together into the larger tool chain. So we have wide community participation here. Also, the tool chain allows you to evaluate different technologies by using simulators and so on before actually building the technology in the lab or pouring lots of money into a certain device before you know if it's going to be scalable. So now I'd like to talk about the details of our design flow in a bit more detail. So the quantum intermediate representation. So a standard intermediate representation might be 3-address code. Well, here this is a very, very different type of representation. Now our intermediate representation is based on the quantum circuit model. And the quantum circuit is made up of qubits, which are analogous to a classical bit, except now they take on the value of 0, 1, or a superposition of 0 and 1. So here we have 2 qubits. And then in quantum circuits, you have only unitary transforms and then measurement. Here I'm not showing a measurement operation. I just have 2 unitary transforms. H represents the Hadamard gate here, and then this gate here is a controlled NOT gate. And this whole circuit performs with, or it makes an EPR pair, an Einstein-Podolsky-Rosen pair. So here, this is the mathematical representation of an EPR pair for different values of x and y here. Now what's important to note about this quantum circuit model is that unlike in classical computing when you would have a single output value on each wire, here in quantum computation, these outputs are actually entangled. So we can't separately look at x and y. These are an entangled output. So you can see how this is going to affect, for example, the optimization phase. It's much more complicated now to optimize a circuit such as this. Well, or that would have the same properties as this quantum circuit. So in the optimization phase, what was previously fairly straightforward to perform, optimization on 3-address code, dead code elimination, people optimization, loop optimization, the optimization now of a quantum circuit is not straightforward. So it is even difficult to know the optimal circuit to represent a 2 to the n by 2 to the n unitary matrix. And only recently, in the past 3 years, have the upper bounds and lower bounds been matched for theta of 4 to the n elementary gates to represent a 2 to the n by 2 to the n unitary matrix. Even more difficult is optimizing circuits involved in error correction. Error correction circuits have a certain property they have to achieve. They have to prevent the spread of errors and also correct errors in the quantum circuit. And so if you optimize and change the order of gates or change the type of gates, the spread of errors through the circuit changes. So this becomes more difficult to optimize circuits in error correction. And these circuits, some error correction circuits are called stabilizer circuits because of the gates that are involved in the circuit. And you see that this, a stabilizer circuit takes O of n squared log n, controlled not Hadamard and phase gates in the output circuit. So what was previously a fairly easy phase is now fairly difficult in our design flow. And this is, so I worked on some quantum circuit optimizations that helped achieve the matching upper and lower bounds with Al Aho. And this work I presented at EQUIS, a quantum conference in Japan. So now we have the quantum assembly language. So traditionally, a traditional assembly language is based on the von Neumann architecture. And now in quantum computing, we don't have a standard architecture. So we're going to keep the assembly language independent of the device at this point. So on the right-hand side, I have a sample assembly code that outputs the same, it computes an EPR pair, the same circuit as I showed on with the previous slides. So our assembly language is a typed assembly language. We have 3 types. We have a qubit type, a classical called C-bit type, and then we have gate. And you see here we declare we have 2 qubits, X and Y. We declare that gates, a Hadamard gate and a C0 gate, written as CX. And then we perform these gates on the qubits. And again, quantum instructions are solely unitary transforms, unitary gates and measurements. But in our quantum assembly language, we can also make classical calls for a complete classical instruction set. Andrew Cross and I have developed this Chasm assembly language. Yes?
So when you say for a complete classical instruction set, won't the instruction, I mean, in that case, it could very well be technology dependent. I guess this isn't really an assembly language at the point.
Right. We call it an assembly language, but it's not identical to what you think of as a classical assembly language.
So you're going to have to do another level of optimization when you
right. Right. So Chasm lies here in our design flow between the technology-independent optimization and technology-dependent optimization. And within our optimization phases, we assume we have code generation. So Chasm is made up of a certain set of unitary gates. And according to the device, we might need to translate into a different set of unitary gates. And so that would be done in the technology-dependent optimizer. It would generate physical operations language code with a specific set of gates that can be computed on the specific device. And it would be optimized for a certain, maybe certain gates can't be computed on the device, so you optimize over certain gate sets, number of qubits, etc. So the objective function of the optimization phase can change according to your device, number of qubits, number of gates.
So what's the value of the quantum assembly language stage? It seems to me that since you may have to do that, I mean, you may have to, essentially you have to re-optimize it to, sort of undo a lot of the optimization that you've done previously. What advantages there that makes that?
Right. So between the quantum intermediate representation and the Chasm code, in the technology-independent optimization, we've actually changed in QIR, we actually assume that it's a universal set of gates. It can be any gate. Whereas in Chasm, we assume that we now have changed to a discrete set of gates. So this is one of the differences between QIR and Chasm. They might very well resemble each other very closely. QIR and the high-level languages are open research problems at this point.
So, for example, translating into classical assembly language the classical steps isn't actually necessary for the QASM step.
Right.
You might as well just leave all of that.
Right. That can just exist in a separate. You've separated out the quantum and the classical instructions somewhere along here, and so the classical instruction set sits separately from the quantum instruction set. What we're doing in this design flow is just trying to optimize, for example, just the order function call in Shor's algorithm. So we're converting that into Chasm. So and then you would reassemble the classical pre and post processing instructions, and then this quantum set of instruction would be passed to the quantum device. But there has to be some communication between the classical and quantum device, and the exact setup of that is still undecided. So we've just separated it out at this point. Right, so the optimization phase, you have different objective functions that you can optimize over. And in the technology-dependent optimization phase, you switch to a gate set that would be doable on the actual quantum device that you're going to send to. So for example, one possible technology is the ion trap. There are many possible technologies being researched currently in labs across the world. Ion trap is one. Others are quantum dots, NMR, which isn't scalable, but people have looked into that. But here, I'd like to talk about the ion trap. And this is a device simulator that has been built at MIT under Ike Chuang and his students. And Ike actually helped build the world's first quantum computer, which was NMR-based, and it can factor the number 15 into 5 times 3. So it's not quite scalable yet. But he did work on that, and he feels that the ion trap is a very promising technology. So up at MIT, he's working on building the ion trap and different components of the ion trap. So the simulator helps him and other physicists visualize what's going on in the device and also determine what kind of failure rates will occur before he actually builds this in the lab. So the simulator, just to tell you what this is for the ion trap. The ion trap lies in some layout. In this case, this is called an H-tree layout. So this is the ions represent the qubits, and they sit in locations. And then they have to move along channels in the trap in order to interact with other ions. So these ions might move up here, sit here, and then they're adjacent to other ions. In an ion trap, in order to perform a multi-qubit gate, like the controlled NOT gate, ions have to be adjacent. So we call this a local setting. They have to be local. So these ions are local, and then these flashes are gates being applied. So in an ion trap, a gate is applied by a laser. So these lasers hit the ions, perform a gate, and then you have ion traps also require things like cooling and joining. So they have to cool the ions, join the ions into a chain so they can interact, and so on. And then they would move back along these channels. This is just an overview of what an ion trap looks like. So the simulator provides a visualization for the physicists of what's occurring actually in the ion trap device. So in order to build our design flow, Ike invited me to MIT to work with him and his students and to learn more actually about the ion trap, since if we're going to build a design flow, we have to understand both the source language and the target device. So I worked at MIT last year with Ike on the design flow and also on different error correction schemes. But again, this is just one type of device that might lie on the back end of our compiler. And then the physical operations language would be provides the machine instructions that are then passed to the actual device or simulator. And again, since the architecture is not set in quantum computing, we will have many different QPOLs, many different physical operations languages for the different devices that we might have. And the physical operations language, it takes into account the layout, the geometry of the architecture. In this case, the grid for the ion trap. You see that we're declaring the ion as a data type ion, and it's going to lie in this location. So we have layout instructions, and we have other system-specific instructions as well, such as cooling and joining, which isn't shown in this snippet of code. But we also have movement, as I discussed in ion traps. The ions have to move together to interact. So we have a movement operation here, and this is a snippet of code that also prepares an EPR state. As the circuit I showed earlier does. So what we've seen is that we can abstract the physical system into a mathematical model, which we can then pass along our design flow. We can take the mathematical model and come up with a computational formalism, or a quantum circuit model, that represents the mathematics of our quantum algorithm. And then we can translate this into an intermediate representation and an assembly language down to a actual physical operations language, the machine instructions, to pass to the physical system, which eventually, in this case, is laser pulses applied to ions in an ion trap. So here, this is just a review of taking the mathematics to the quantum circuit and then down to our different machine instructions and eventually to the physical device. Now, the big question, I took this design flow to David DiVincenzo and Barbara Terhal at IBM. And the big question for them was, well, this is great, but where along this design flow do we put in error correction? So quantum computing, the components in a quantum device are inherently noisy. So we have to, for a scalable device, we have to have quantum error correction. We have to have fault tolerance. This is very different than in a classical setting where CMOS is naturally robust. So what I'd like to talk about now is where along this design flow should we put fault tolerance and quantum error correction, and what does it mean to do quantum error correction? How is it different than classical error correction? And I'll show you that. So is quantum information processing scalable? So here, this orange line represents a quantum gate, and here we have the magnitude of a perturbation of a quantum state, or the magnitude of a perturbation of a voltage on a transistor, versus the probability that the circuit fails after applying that gate in the technology. So in the quantum case, this has a linear relationship, and in the CMOS case, it has a much more desirable curve. So what we want to be able to do is, with some mechanism, some means, we have to take this orange line and we have to push it to resemble the red curve here. And how do we do that? So what we can do to make the quantum gate more reliable is we can add quantum error correction. So you can see that by adding quantum error correction, the previously linear line now resembles the red curve, which is exactly what we need to produce a robust quantum computer. So in quantum error correction, you can have different levels of coding. This is called concatenation. This is just one approach. You could have a large block code as well, but today I'm going to talk about concatenation in error correction. So what this means is we can have less coding or we have more coding. And if we have more coding, if we're below some threshold, the threshold here means that if our error rates of our components in our quantum circuit or our quantum device are below this value, this vertical line here, then actually adding quantum error correction will make our circuit more reliable. But if we're above that point, above that threshold, then our quantum circuit actually becomes noisier with the addition of quantum error correction. So we want to be able to determine what this threshold value is so that we know or guarantee that error correction is actually making our device more reliable. And we want to know that failure rate of the component that's necessary so that when we try to build a device in the lab, we have a target error rate. And if we achieve that target error rate or below that target error rate, then we know our computation is going to be scalable and reliable. So if we have less coding, you can see that by adding more coding above the threshold, more coding could actually make it even noisier, not better. So I want to talk about how we can theoretically analyze what this threshold value is in a quantum, for our quantum devices. So the elements of fault tolerance in a quantum computer, well, we know that we have to have fault tolerance, which includes quantum error correction. We have to have fault tolerance for scalability. Our components are too noisy if we don't have fault tolerance. And we can achieve fault tolerance by using what's called concatenated coding, concatenation. And this is the method I'm going to talk about today. And then we also have the threshold theorem, which says that if our components are below a certain failure rate, then even though they are faulty, we can still achieve a reliable, robust computation. And in addition to thinking about fault tolerance just in general, we have to also take into account whether or not locality is essential in our architecture. So do we have to incorporate movement? So we have to think about the geometry and the layout of the device that we're going to be using. So classically, if we have a NAND gate, you can say that this NAND gate fails with probability P. Then we can use triple modular redundancy encoding to make this NAND gate more reliable. So this is how we make the NAND gate fault tolerant, is we replace a single NAND by 3 NANDs. In other words, what we're doing is we're encoding the data. A single 0 bit is encoded in 3, and a single 1 is encoded in 3 1 bits. So for the NAND gate, then, we repeat the NAND 3 times, and then we're going to follow it by these 3 majority gates. Now this performs the same task as a single NAND gate. We assume that each one of these gates fails with probability P. And then what happens is now, previously the single gate failed with probability P. Well now, this circuit fails only if two gates fail. Yes?
I may be nitpicking, but it seems if a majority gate fails, for example, it can produce funny output that we can consider a success or a failure.
Well, then you look at you have to decode these 3 bits again.
But it's another gate, right?
Right, but it's not. This is going to improve the reliability of your circuit. So previously, so now the probability of failure of this whole module is less than or equal to 6p squared, because we have to have 2 components failing, and there's 6 ways for these 2 to fail. So if p is less than or equal to 1 over 6, then this module is more reliable than the single NAND gate, and we should use this instead. Now we can repeat this process again, so this is called what we call concatenation. So we repeat again, we replace each of the 3 NAND gates before with the entire module. So now we have a level 2 encoding, and it's a recursive construction. So we replaced 0 with 3 zeros before, now each of those zeros gets replaced by 3 zeros, so we have 9 zeros and 9 ones representing 0 and 1. And now this circuit fails only if 2 modules fail. So 2 of these big dashed boxes. So we can see again that the probability of failure of this whole circuit is now less than or equal to 6 times 6p squared, which we get by just plugging in. And then the probability, we can say that the probability of failure is less than or equal to cp to the k over c. So I just plugged in for 6. C was 6. 1 over c is 6. So now what we can do is we derive the fault tolerance threshold theorem. And this was actually done by von Neumann in 1956. So this is not new to the classical community. So using k recursive levels of error correction, in the previous slide I showed 2 levels, we get this result, where the probability of failure of the entire circuit over the threshold is equal to, this is the initial gate failure, the initial failure of any component in the circuit over the threshold, and then k is the level of error correction. So this carries over to the quantum setting as well. So the threshold theorem is that we can achieve good, reliable computation with faulty components as long as the error rates of the components are below this threshold value p thresh, which is 1 over c, as I showed in the previous slide. But in quantum fault tolerance, we can't exactly just copy do redundancy codes as we did in the classical case. In the classical case, we used a TMR code. In quantum fault tolerance, we can't do that. We can't just copy the information. Well, for one reason is because there is no copying allowed in quantum computation. So we cannot duplicate a quantum state. Also, it's now more difficult. In the classical setting, we had bit flip errors. In the quantum setting now, we have a continuum of errors on each qubit. But luckily, we can discretize these errors and just look for bit and phase flip errors. But already, bit and phase flip errors is more difficult than just bit flip errors. And in addition, if we measure our quantum information, then this destroys the quantum state. So we can't look at our computation, we can't look at our data and ask what errors are on our data. We have to have some other means of transferring those errors somewhere else, which what we're going to do is we'll spread the errors onto what are called ancilla bits, which are like work bits. And so we can overcome this obstacle of measurement by measuring work bits, because we don't care if we destroy their state, as long as we see what the errors were on the data beforehand. So now I'd like to talk a little bit about what quantum error correction is. So in this talk, I'm just going to focus on 713 error correction. So what this means is that we take a single qubit and we encode it in 7 qubits, and it's a distance 3 code, so it can correct just one error. So this is an example of what error correction looks like for quantum computing. So our data sits on this upper wire, and the slash means that actually it represents 7 qubits in this case. So we have 7 qubits that we want to error correct. And what we can do is all of these 0 states, all of these 0 qubits are work qubits, they're ancilla. And we can use them to read or to determine what errors actually lie on the data. And we do this by preparing them. The G network is a preparation, and then V is a verification network. And all of these boxes include many gates inside them, much circuitry in each box. So we prepare and verify that our ancilla qubits are in some state. And then this S box is called syndrome extraction. We can extract syndrome information from the data, so we can spread the errors that were on the data down to the ancilla, and then we can look at the ancilla by measurement and determine what errors were on the data. And then, using this information, we can control the recovery, some recovery process to the data, by applying some quantum gates back on the data so that we restore the data to the state we want. So in more detail, the preparation network looks something like this. So it consists of several Hadamard gates and several controlled NOT gates. So we prepare our ancilla into this 0 logical state. And then we verify that it's in this state by using controlled Z gates, Hadamard gates, and then measuring to check if we're indeed in this state. So you can see that error correction is quite complicated, and it involves adding a lot of gates to our circuit. So what we want to do is we want to be able to determine a method to replace each gate in the quantum circuit with its fault-tolerant procedure, so that then when we put all of the gates together, the whole thing is fault-tolerant and reliable. So what we've done is I've come up with the replacement rule model with David DiVincenzo and Barbara Terhall. And the idea is that a quantum circuit consists of many types of locations: control NOT gates, Hadamard gates, measurements, many different types. And what we want to do is we want to replace each location in the original circuit by its fault-tolerant version, which means that we replace it by error correction, so that we correct the errors before they get to the gate, and then a fault-tolerant implementation of the original gate. And we can do this repeatedly to obtain the concatenated version of the original circuit. And we do it recursively, say, k times. So what this looks like is, say we have a 2-qubit gate U. For example, it could be a controlled NOT gate. And it acts on qubits P and Q. Well, in the 713 code, we replace each qubit, we encode it in 7 qubits. So the a single P qubit becomes 7 qubits, and similarly for the Q. And then what we want to do is we want to error correct these qubits before we actually perform the implementation of the gate, so that we remove some of the errors so that when they reach the gate, they don't spread. So error correction here, in this case for a 713 code, it'll correct a single bit flip error and a single phase flip error in each one of these boxes. And again, this E is the entire circuits I showed earlier with many little boxes.
When that thing recursively looks like that, that will blow up the circuit size.
Exactly. Yes, if you recurse too many levels of concatenation will never be practical. But the idea is you want to find what level of concatenation will achieve the reliability you need in your quantum device. So maybe just one level, a large block code, if you have a code that can correct many errors, so a larger distance code would be a much better idea here, as long as you don't have too many qubits involved, that it becomes too costly.
To really do that optimization, don't you need to know something more about the sort of likely failure models? I mean, basically...
The noise models?
Well, yeah, the noise models are sort of how problems are clusters. I mean, do qubits sort of fail individually, or is it likely that connected qubits would fail, so that sort of then take a path through the concatenated circuits, and that's likely what's to go out? Or is it like a
So there's obviously in different technologies, different things are going to fail differently because you make a qubit, like for example in ions, you have random field fluctuations. I think that's one of the predominant noise causes. So you have different noise causes in these different technologies. But you can assume that just for achieving a ballpark threshold estimate, the idea here is most likely this replacement rule won't be used exactly as it's written here. But this provides a theoretical argument for why quantum computation could indeed be scalable. So we want to just perform a general assessment of what the threshold might be for the different components of the quantum circuit. So you just assume that different gates fail independently with some probability of an X, Y, or Z error, so bit flip or phase flip or some combination of bit flip and phase flip errors. And so using these assumptions, you just achieve a ballpark estimate of the threshold. But obviously in quantum computing, there's many other types of noise than just that failing. So you have different interactions with the environment, you have different crosstalk. Crosstalk is a big problem. So accounting for these, you actually need to use many different methods than just quantum error correction. So many of those, protecting against those types of noise, mostly the physicists are working on right now. But what we want to be able to do is just guarantee that even the quantum circuit is going to be reliable. Because at this point, if you don't have error correction and you don't have fault tolerance, and one of the gates fails, then your whole computation is likely to fail because of how errors spread throughout a circuit. So we just, from a theoretical standpoint, want to be able to prevent the spread of errors. And then this will be one level of the process to achieving a robust computation in general. So, right, so then we have a fault-tolerant implementation of the actual gate. And we do this in a way such that it doesn't spread too many errors. Because if we have too many errors on one block of these qubits, then those qubits are, they're just incorrect, they're worthless. So we want to prevent the number of errors in each block of these qubits. And we do this by doing a fault-tolerant implementation of this gate. And for a 2-qubit gate in certain codes, this means a transversal implementation, which is just a bitwise implementation. So we'd perform a C0 between P0, Q0, P1, Q1. And this would prevent the spread of errors from P0 to Q3, for example. So for each type of location in our quantum circuit, we have such a replacement rule. And again, E and the way we do U is dependent on the code. So in different codes, it's difficult sometimes to find a good implementation. That's why for now we're sticking with the 713 code, because it has nice representations of the gates when we have to do them fault tolerantly. So as I said before, we have two types of architectures. We have an architecture where the qubits have to be adjacent to interact, and then we have an architecture where there's no restriction on the distance between the qubits to perform a multi-qubit operation. So clearly, if we require that qubits have to be spatially adjacent, this is going to change our replacement rules. So a question we also want to ask is, does there exist a threshold in the local setting when we require movement? And if the threshold exists, what is this threshold? Because, for example, an ion trap, it wasn't known if it was going to be scalable, if there actually was a threshold, because there was all this movement required. And when you concatenate, there's even more movement. So with all of this movement, do we still have a threshold? And this is what I'd like to talk about now. So with David DiVincenzo and Barbara Terhall, I wanted to answer this question of how locality exactly affects the threshold. And this is work that we published in Physical Review A, and we also presented at QIP, which is the quantum conference. So the idea here is that let each of these boxes, these larger boxes, represent a single qubit that's been concatenated once. So each single qubit is now represented by 7 data qubits, and say the 7 data qubits sit in this light gray area. And then, as you saw in error correction, we require a lot of work qubits to perform error correction. So these qubits sit in the middle here, this white box. So each of these qubits now, on the next level of concatenation, each one is encoded in 7, and then all of these now require ancillas for error correction. So upon concatenation again, each of these light gray data qubits is now in one of these larger boxes here. And all of them have their ancillas for error correction. And then the ancillas on the middle are now concatenated again as well. And so then they have their ancillas for error correction also in the middle. And the darkness of the gray indicates the amount of moving that needs to be done. So here, these light gray qubits, they had to move distance, say, order r. R is some scale factor of the distance. Now, at the next level of concatenation, they have to move distance r squared. And so on, up to k levels, they have to move distance order r to the k. So you can see that this is a problem. If you have to concatenate to high levels, you have a lot of movement you have to consider, and movement is noisy. So we have to require that error correction is done in transit. And you also have to have the space in your layout to account for all of this additional error correction. So what we'd like to do is see how locality affects the threshold. And you can see previously it's been, these are threshold estimates the year versus the actual threshold estimate, just over the past 10 years. And you can see that people have estimated in the mid-90s, late 90s, most of the threshold estimates were between 10 to the minus 5 and 10 to the minus 6. So a component of a quantum computer failing at the rate of 10 to the minus 5 would be reliable. But you can see that in recent years, actually, the threshold has gotten a lot better, and that these estimates by Steen and Reichardt are closer to 10 to the minus 2 and 10 to the minus 3. Now, if I have a quantum computer that has a failure rate, or the components fail at a rate of 10 to the minus 2 or 10 to the minus 3, and I build this, I put my quantum algorithm on it, I want to guarantee that it's actually going to be reliable. So I want to know why there's this discrepancy between these recent threshold estimates and previous threshold estimates. So what is the real threshold? So what Barbara, David, and myself did is we came up with a new analysis method to more accurately determine what the threshold should be for both the non-local and local architectures. So these I talked about different levels of concatenation. These are all for the 713 code, the same code. But some of these threshold estimates are achieved by looking at only one level of concatenation. So what's the failure rate after one level? And if you recall, I showed the graph where more coding could lower your threshold further. Well, if you so it's not. So some of these look to high levels, some look only to low levels of concatenation. So what we did is we developed this replacement rule model that determines how locality actually affects the threshold. And what we do is we use these replacement rules as I showed, and we recursively apply them. And we develop an analysis of each replacement rule, determine how each replacement rule would fail, and then we estimate the local and non-local thresholds for the 7-qubit code. So as an overview of our analysis, what we do is we look at the probability of crash, or this failure probability function, for each location type's replacement rule. So for the replacement rule for a Hadamard gate, replacement rule for a CNOT gate, and so on. So at each level k, you use the location failure probabilities from the previous level to determine the location failure probability for the current level. And you plug into this failure probability function that we come up with. And then you can determine at each level of concatenation what the reliability is. So what does this mean? So again, this is the circuit for the EPR pair. If at the first level, Hadamard fails with failure probability gamma 1, and the C0 fails with probability gamma 2, then we apply our replacement rules. And so these dash boxes represent the replacement rule. We have error correction plus the gate. And again, these are operating now on 7 qubits, so this is these are transversal gates. Then we can use the failure probability function for this original Hadamard location for the replacement rule and achieve the new failure probability of the whole dash box, which is gamma 1 prime, and then the new failure probability of this whole dash box, gamma 2 prime, and so on. So we do this for each type of location, and we do this recursively. So then we repeat. Each gate in this box is replaced by the dash box, and so on. We do this to a high enough level so that we can determine if the original failure probability vector, gamma 1, gamma 2, was above or below threshold. So we start with the vector of failure probabilities of the locations. So this has the initial failure probabilities for all the components of our circuit, and we map this onto the next, onto gamma of 1, and so on, up to a high enough level, a high enough k, so that we can determine if the initial failure probability initial vector of failure probabilities is above threshold or below threshold. It's below threshold if it heads to 0. It's above threshold if it heads to infinity. And again, we have a failure probability function for each type of location. So just to give you an idea, it's a very high-dimensional map. In the non-local case, we have 5 types of locations in our circuit. So we have a 5-dimensional map. And in the local case, we now have to incorporate movement and different types of weighting and so on. And this becomes an 8-dimensional map. And more recently, we've looked at a more explicit local architecture where it's actually an 18-dimensional map. So it's a very high-level map, but we can still determine the thresholds from this. So this is a graph of the failure probability of a single qubit gate versus the failure probability of a 2-qubit gate. These are the initial settings. So initially, the whole vector is set to the failure probability of a single qubit gate, except a weight gate is 1/10 of that value. So what this means is that here we have 3.9 times 10 to the minus 4 is the initial failure probability of the components. Now, with one application of our map, the failure probability falls to around 1.1 times 10 to the minus 4. So you can see that it's heading towards 0. It's decreasing. So if we had stopped here, if we had cut here and we only applied one level, then we might think that this was actually indeed below threshold. So this gives you some idea of why the threshold estimates lie in different, or there's a discrepancy between previous threshold estimates. But at the next level, you can see that we apply our map again, and it's now actually starting to go up. And again, it's going up, and so now it's heading to infinity. So it takes this big turn. So actually, 3.9 times 10 to the minus 4 is above threshold. And if we had built our quantum computer with that failure rate, it wouldn't be reliable. And similarly for 3.7 times 10 to the minus 4. But then for 3.5 and 3.3 times 10 to the minus 4, you can see that after one iteration, it's going down, and then after another iteration, another level of recursion, it continues to go down. So in this case, 3.5 and 3.3 times 10 to the minus 4 are both below threshold. So you can see that we have to look at high levels of concatenation to determine what the real threshold is. And it's also important that you look at many of the different types of components that are in your circuit, because a weight gate might be much more reliable than a single qubit gate, but if you determine that the whole circuit can fail at the failure probability of the weight gate, then your circuit's not going to be reliable. So it's important to account for these different types of locations and actually have a 5 or 8-dimensional map. So you can see that then our threshold estimates, we do this for the local and the non-local case. We achieve a threshold estimate around 10 to the minus 4 for the non-local setting and around 10 to the minus 5 for the local setting. So you can see that these threshold estimates might indeed be inaccurate, or what we call pseudo-thresholds. It's a fake estimate. It's not a real threshold estimate. It won't give you an accurate or reliable computation. And recently, our results have been further, Alaferis and his colleagues have found a lower bound, and it is indeed closer to our threshold estimates. So this has been partially confirmed. So what we did is we performed the first assessment of how exactly locality influences the threshold, and we further showed that there does exist a threshold for a general local layout. And our method, we can use this method of analysis to determine the threshold for each type of technology and error correction code, so that now we can evaluate different error correcting codes and different error correction and fault tolerant schemes. And we can also evaluate different architectures in advance of building them in a lab. So back to the design flow. So we have this, so now we know how to perform fault tolerance and quantum error correction, but we still don't know where in the design flow this should go. So it could possibly go at the software level, or perhaps it could even go at the hardware level. So it's an open research question where in this design flow we should place fault tolerance. In software, we could apply something like the replacement rule model, and then generate the technology-dependent code. And then we could possibly use scheduling algorithms and different layout tools that preserve the fault tolerance. On the other hand, we could look at a more hardware-based approach, and we could apply fault tolerance in a way we would create universal fault-tolerant device-specific components, and then we'd publish how to connect these components, and this would be another method of achieving fault tolerance and error correction. But in reality, I believe it's going to be some combination of a hardware-based approach and software-based approach. For example, we might require a different type of code altogether. We could actually look at a more physical-based code, like a topological code, which would be more of a hardware-based approach. So in conclusion, I've shown that theoretically, quantum computing can be made reliable and scalable, which is good news. But I've shown that in order to achieve this, we require a design flow that transforms this quantum algorithm written in a high-level language into the machine instructions for the quantum device. And I've shown that this design flow is indeed very different than the standard compiler you have for your classical computer. It requires very different intermediate representations, such as the quantum circuit model, and different optimizations for the optimization phases. In addition, we require fault tolerance and quantum error correction. And one way to analyze different error correcting codes and fault tolerance methods is to use, for example, the replacement rule model and the analysis method I discussed. It also requires, well, these fault tolerance threshold analyses can help then physicists develop quantum devices. It can give them a target error rate. If they can achieve such a target error rate, they have a better idea of whether or not they'll be able to achieve reliable and scalable quantum computation. So this is great news, but we still need an actual physical device with a low failure rate and a long coherence time. And of course, this is quantum computing, it's a very long-term research project. Physicists tend to like long-term projects. So this is one of them. We also need many more qubits. So we have quantum error correction techniques, but as we concatenate, it requires many, many qubits the further we concatenate. If we use a large block code, it still requires many qubits. And just Shor's algorithm without error correction requires thousands of qubits. So we need many more qubits in our quantum device. And then we also need quantum error correction methods that have better error correcting properties, whether that be encoding with fewer numbers of qubits or detecting and correcting against higher numbers of errors. So all of these things will be necessary to achieve a reliable, scalable quantum computer. Thanks. Yeah?
Now, a few slides back, you distinguished between threshold and pseudo-thresholds, where for a few iterations, everything improves and then they go bad again. If I never do more than 3 combinations, why could I care?
Right. Well, actually, it's a good point. Because in the lab, when you actually build the physical device, you might only do 2 or 3 levels, and maybe at the 4th level it goes up. So in that case, yes, you want to, for building a device, you don't care if it goes up after a certain number, but you need to know if it goes up after a certain number, in the sense that if you concatenate further, it might become unreliable if you didn't know that that threshold was really above threshold in the sense of how I've defined above and below threshold. So from a theoretical standpoint, we want to know what the guaranteed threshold rate is. But for actually building the device, you want to know what levels of concatenation are necessary to achieve the reliability you want. So yes, it's a very good point.
Any other questions?
Yeah.
We get more sense of like these ion trap devices. I mean, what's their status in terms of experimentalists trying to build them?
Right. So there's a group in Switzerland they're making good progress. They have, I think they can achieve 10 qubits right now, can stay coherent, remain coherent for a small amount of time. I'm not sure the exact time scale. And recently, actually, they were able, if you remember in the HT layout, you have these channels, and you have to turn around 90 corners. And actually turning qubit ions around a 90-degree corner was actually very difficult. And recently, they were able to achieve that. At MIT, what they've been working on is actually the lasers, controlling the lasers, which is another large problem in ion traps. How do you control the lasers and precisely target a single ion in this large ion, well, small ion trap, but in the larger ion trap. So they've been working on tuning these lasers and applying just very specific gates. And they have achieved, not at MIT, but another lab, they've applied C0 gate and so on. It's slowly coming along. I think the reliability, the concern is clearly numbers of qubits and how you're going to fit that many qubits and act on them independently. I think that's one of the major problems right now. But I think they're slowly making progress on this. I think ion traps are very promising as a technology for quantum computing.
I mean, sort of the feature size of those ion traps is a couple of angstroms, right? I mean,
It's really tiny, yeah. But so then when you can extend the computer by connecting ion traps together. The problem is that with quantum error correction right now, not to sound negative, but if you required right now, with the current reliability of different components of the ion trap system, you'd actually have to have so much concatenation, I think like 7 levels of concatenation, which would cause your ion trap to be the size of a football field, which clearly isn't practical. But, I mean, of course, you're not going to use the 7-qubit code in reality, in practice. You're going to use something else. So this is a very long-term project, obviously. And so any small step is really, it's a big step, just moving around a corner or just keeping the qubits coherent for some amount of time. So. Oh, did you?
Okay, thank you.
Thank you.